Hello guys, hope you're doing well. Today we want to understand the derivative of absolute value functions. First, remember what the absolute value means. The absolute value of a number is its distance from 0. For example, the absolute value of 3 is positive 3, and the absolute value of negative 3 is positive 3. So the absolute value always gives a non-negative result, right? So always remember, finding the root of the expression inside the absolute value is the key. So here's the trick. For any value greater than the root, the expression inside is positive. So we simply remove the absolute value bars and write it as it is. But for values smaller than the root, the expression becomes negative. In this case, we remove the bars and multiply the whole expression by a negative sign. Now look at the function. F of x equals the absolute value of x. To understand its derivative, we write the absolute value in a piecewise form. Means the absolute value of x equals positive x if x is greater than or equal to 0 and negative x if x is less than 0, right? Now we differentiate each part. If x is greater than 0, so f prime of x is positive 1, and if x is less than 0, so f prime of x is negative 1. But what happened at x equals 0? From the right side, the slope is 1, and from the left side, the slope is negative 1. Since these two slopes are different, the derivative does not exist at x equals 0. So the function has a sharp corner at 0. Let's do another one. Find the derivative of f of x equals the absolute value x minus 2. First write it in piecewise form. The absolute value of x minus 2 equals x minus 2 if x is greater than or equal to 2 and negative x minus 2 if x is less than 2, like this. Now differentiate each part. F prime of x equals 1 if x is greater than 2 and negative 1 if x is less than 2, like this. So at x equals 2, the derivative does not exist because the slope from the left and right are different. So the derivative is f prime of x equals positive 1 and negative 1. Okay guys, this is the basic idea of derivatives for absolute value functions. But there are a few more important things to know, and we'll go through them together by solving some examples. Let's do it. Okay guys, let's look at how we check differentiability using the limit definition. We have two functions here, and we're gonna test both of them at their root, which is x equals 1. First, let's look at f of x equals the absolute value of x minus 1. To find the derivative at 1, we use the formula. Means f prime of 1 equals the limit of f of x minus f of 1 over x minus 1 as x approaches 1. Since f of 1 equals 0, it simplifies to f prime of 1 equals the limit of the absolute value of x minus 1 over x minus 1 as x approaches 1. Now we have to check this from two sides. First from the right, means 1 from the right. The expression inside the absolute value is positive, so we have x minus 1 over x minus 1, which equals 1. And from the left, means 1 from the left, the expression is negative, so it becomes negative x minus 1 over x minus 1, which equals negative 1. Okay? Because 1 and negative 1 are not the same, the limit does not exist. So f of x is not differentiable at x equals 1. Now let's try the second one. f of x equals the absolute value of x minus 1 whole cubed. we use the same formula, means f prime of 1 equals the limit of f of x minus f of 1 over x minus 1 as x approaches 1. And again, we know that f of 1 equals 0. So we have f prime of 1 equals the limit of the absolute value of x minus 1 whole cubed over x minus 1 as x approaches 1. Okay? To make it easier, let's break. Means the absolute value of x minus 1 whole cubed into x minus 1 whole squared times the absolute value of x minus 1. Now the limit looks like this. The limit of x minus 1 whole squared times the absolute value of x minus 1 over x minus 1 as x approaches 1. Okay? Now we can cancel out 1 x minus 1, which leaves us the limit of x minus 1 times the absolute value of x minus 1. Now if we plug in 1, the whole thing becomes 0. This is true for both the left and the right side. So in this case, the derivative does exist and f prime of 1 equals 0. So what is the difference? In the first example, the power was 1. So it created a sharp corner. But in the second example, the power was higher than 1, which smoothed out the graph at the root, making it differentiable. So remember, higher power roots are usually differentiable. Okay? Now let's solve another example. Okay guys, let's look at this example carefully. It's very important. Determine the number of points at which the function f of x is non-differentiable. To find where it's non-differentiable, we need to check two places. First, the domain constraints where the function might be undefined, and second, the transition point at x equals 1. First, let's look at the denominators. In the first part, the denominator is x minus 2. It becomes 0 at x equals 2. But x equals 2 is not in this domain because x is less than 1. And in the second part, the denominator is x plus 2. It becomes 0 at x is negative 2. But x is negative 2 is not in this domain because x is greater than or equals to 1. Right? So the function is continuous in its domain. No issues here. Now let's check the boundary at x equals 1. A function is differentiable only if it is continuous and has the same slope from the both sides. First, let's test for continuity. Left hand limit means x approaches 1 from the left, means less than 1. So if we plug in 1 for x, in the first part we have f of 1 is equal to the absolute value of 1 plus 1 over 1 minus 2 equals negative 2. Right hand limit means x approaches 1 from the right, means greater than 1. If we plug in 1 for x, in the second part we have f of 1 is equal to the absolute value of 1 minus 1 over 1 plus 2 equals 0. Since the left hand limit does not equal the right hand limit, the function has a jump discontinuity at 1. So here's the golden rule. If a function is discontinuous at a point, it's automatically non-differentiable there. So we don't even need to calculate the derivatives because the function jumps at 1. It's definitely non-differentiable at that point. So there is only one point where this function is not differentiable. Okay guys, let's look at this example. For the function defined as f of x equals the absolute value of x squared minus 1 when the absolute value of x is less than or equal to 2 and 2x minus 1 when the absolute value of x is greater than 2. In how many points in the function f of x not differentiable? Let's solve this problem together. First, let's rewrite the function in this form. In the first part, we have the absolute value of x squared minus 1 and we can rewrite the absolute value of x is less than or equal to 2 as x is between negative 2 and 2. Now let's look at the second case. We can rewrite the absolute value of x is greater than 2 as x is greater than 2 or x is less than negative 2. Now we must check the connection points. Let's start with x equals 2. The limit from the left means less than 2 is in the first part equals the absolute value of 2 squared minus 1 equals 3, and the limit from the right means greater than 2 is 2 times 2 minus 1 equals 3. So it's continuous because the left hand limit and the right hand limit equals 3 equals f of 2, right? Let's check the derivatives. For the left means x is less than 2. When we plug in 2 for x squared minus 1, so x squared minus 1 is positive. So the absolute value of x squared minus 1 equals x squared minus 1. So the derivative of x squared minus 1 is 2x. And if we plug in 2 for x, we have 4. Means the slope is 4. For the right means x is greater than 2. The derivative of 2x minus 1 is simply 2. So the slope is 2. Since 4 is not equal to 2, the slopes don't match. So the function is not differentiable at x equals 2, right? Check the other boundary at x is negative 2. The limit from the right means greater than negative 2 equals the absolute value of negative 2 squared minus 1 equals 3. And the limit from the left means less than negative 2 equals 2 times negative 2 minus 1 is negative 5. Since 3 is not equal to negative 5, the function is discontinuous. It has a jump at x is negative 2. And as we know, if a function is not continuous, it's definitely not differentiable. Now let's look at the expression inside the absolute value. Means x squared minus 1. So let's set x squared minus 1 is 0. This gives us plus or negative 1. Since both 1 and negative 1 fall within our domain because x is between negative 2 and 2, we have 2 points of non-differentiability right here because these are simple roots. So x is 1 is sharp corner, x is negative 1 is sharp corner, x is equal to is mismatched slopes, and x is negative 2 is discontinuity. So there are 4 points in total where this function falls to be differentiable.